Hello friends, welcome to UGC PG Pathshala on Quantitative Methods in Geography. I am Aslam Mahmood from Jawaharlal Nehru University, former professor from Jawaharlal Nehru University. Today's topic of discussion is measures of dispersion and moments prepared by Professor Surender Singh of Northeastern Hill University, NEHU. It has been stated several times in the earlier modules that the values of mean of two or more distributions may be same, but the spread of the values in a distribution may vary. It is also an important characteristic of distribution and useful for prediction, fluctuations, variations, and even for analyzing the extreme of variability of geographic phenomena. The statistical term of such variable phenomena is called dispersion, which is measured in two ways. Number one, distance of a particular value from another observed value in a distribution and difference of the observed values from the central point in the distribution called deviation, that is statistically known as mean deviation and standard deviation. The simple measurement of dispersion is known as range when the difference between the maximum and minimum values of a variable is calculated. It is a crude form of dispersion. The coefficient of range R is simple and it is the ratio of the difference of the highest value H and the lowest value L with their summation as given below. That is, R is equal to highest value minus lowest value divided by highest value plus lowest value. It will always be the lesser than unity for a distribution in case the values of the observations of distribution vary significantly. Figure 1. Interquartile and interdecile range may also be calculated by the highest and lowest values of a sector of distribution. Figure 1. Range of distribution of rainfall at Cherrapunji, measure of deviation, mean deviation and standard deviation. Measure of degree of variability in a distribution is relatively used as the sum of the deviations of an observed value from a specific point of distribution. If distribution is measured as average of the absolute value of the sum from mean value called mean deviation. If the average of the absolute value of the deviation from median is calculated, it is called mean deviation. In many cases, in location allocation modeling, this term is used as P median when solution of mode over space is forwarded by using distance of location from median, centroid, standard deviation denoted as sigma. A Greek letter sigma is the standard deviation, is a standardized form of mean deviation and has several mathematical properties. That is why it is more realistic and accurate measurement of variations and used frequently in a detailed statistical analysis also. By definition, mean deviation, that is MD, is simply the mean of absolute values deviated from mean in the series, while standard deviation is based on the sum of the square deviations of the mean deviated series. Thus, the formula for mean deviation from mean and standard deviation are given below. See, one has to note that in the mean deviation, we take the deviations which could be negative as well as positive, and as negative deviation is a deviation like a positive deviation. So, if we add all the deviations, negative will cancel out the positive. So, this should not happen. That is why we have taken the modulus value of the deviation. Modulus value means you take the absolute value of the deviation ignoring the sign, and then you add them. When you work out the mean deviation, you take the deviations from a given value, take the absolute value of these deviations, add them and divide them by the number of observations. So, that gives you the average of the absolute deviations from a given value. Whereas, the same problem in standard deviation is solved by not taking the negative and positive deviations as such. Rather, first we take the deviations and then we square the deviations. Then what happens when a negative deviation is squared, it becomes positive, and positive deviations after squaring remain positive. So, when we square all the deviations, all of them become positive, and we add them and then divide them by the number of deviations. So, in a way, we for a standard deviation we get the average of the squares of the deviations, and since we are squaring it, we take the root also, under root of this. So, standard deviation can be defined as the positive square root of the average of the squares of deviations from the mean. Now, this has one advantage, that unlike modulus values, which are not capable of subjecting them to further mathematical analysis, the standard deviation values can be subjected to further mathematical analysis, because they are used on purely mathematical operation of squaring, under rooting and summation and subtraction. So, that is why the standard deviation has an edge over mean deviation, and that is why in the subsequent statistical analysis you will find that the application of standard deviation is more than any other measure of variability. Now, if we, as I explained, that because of squaring we take the under root also, if we do not take the under root, then the average of the squares of the deviations from the mean is known as variance, denoted by sigma square. Sigma is a Greek letter, so it is written as summation 1 upon n, 1 upon n summation x minus x bar square. Therefore, mean sum of a square is called the variance. Mean sum of a square, mean, that is the average of the mean of the sum of the squares of the deviations from the mean is the variance. In statistics, it is second moment of the frequency of a frequency. The first moment is the first power of the mean deviation, that is the summation x minus x bar in the modulus form, while second moment is the variance as equation 4, and the third, fourth and so on moments are expressed as mu m. Again, mu is a Greek letter, m is the order of the moment, 1 upon n, that is the averaging of the summation of the mth power of the deviations from the mean. So, this is known as the mth moment. In fact, to be more specific, moment of a series are calculated to understand the shape of the frequency distribution. There are two dimensions of variability of the same distribution. Number one, the horizontal, and it is measured through skewness based on the degree of third degree of mu, that is the third moment, and the vertical tilt in the shape measurement is known as the kurtosis, that is determined by calculating the fourth moment of the distribution. Details of such measurement would be given separately in the preceding discussion. Let us describe here the variance, that is the second moment of a variable, which in the form of a group data with class frequencies. Now, we will discuss here how it is calculated, the procedure for simplification of variance calculation. Let us write the variation sigma square in equation 4 for the sum of the square of the procedure of simplification follows. See here 1 upon n summation bracket xi minus x bar square can be using the algebraic expansion of the square given above. We can write it like this, and it keeps on becoming simpler and simpler, so that in the end you are left with summation xi square upon n divided by summation xi upon n whole square, which is nothing but the mean, square of the mean. In order to get sum of squares of deviations, that is summation x minus x bar whole square, that is equal to the variance sigma n, the above equation can be written, that is, for this is what is actually given above, that without dividing n you get the whole thing simplified as given here, and then you divide it by n, you get the variance. So the equation 4 for variance becomes 1 upon n summation xi whole square minus summation xi square upon n. It is a direct method of calculating variance for standard deviation, or standard deviation. When you take under root of this, it becomes standard deviation. Equation 6, without computation of the mean of a series. Now here the advantage is that as standard deviation is defined, or variance is defined as the average of this sum of the squares of the deviation from the mean. So first you find out the mean, then take the deviation. But if you use the above formula, you do not need to calculate mean first and then do the deviation. You can go ahead everything together without going into the calculation of mean. Now there would be some adjustment has to be made when you work out standard deviation or variance in the grouped form. In the grouped form we have class intervals, as well as without group form we have, if we have the observation with the frequencies, then you can have the same formula with a difference that the deviation is to be multiplied by the frequency as it is given here. And if it is in the group form, in place of x, you take the middle value of the class interval. A group data has class intervals along with the frequencies. Now your formula does not require class intervals. So the class intervals are replaced by the middle value of the class intervals. Of course, when you replace them by the middle value, we commit certain amount of error, that the values less than the middle value and more than the middle values are represented by the middle values. When we use middle values, it brings certain amount of negligible inaccuracies which can be neglected also. F is the frequency. The above expression can be simplified for convenience using the same algebraic adjustment. We can also use the formula with frequency, like here, 1 upon, see in the statistics, when we work out standard deviation or variance, we divide by n. But this is the calculation based on the large number of observation, that is, when we take the data from a census universe. But when instead of large body of data from the universe, we take a sample from the universe, then instead of dividing by n, we divide by n minus 1 and get the calculations done for variance and standard deviation as an estimate of the variance of the universe from the sample. N is the number of observation. Now, there used to be a time when shortcut methods were very well incorporated in the syllabus of statistics because it saves time and is used when your data is very big, very large data, very large figures. But after the advent of high-speed computers, etc., it almost has become redundant because nowadays not many people calculate it by hand. It is left to the computer, computer does it. So, for computer it does not matter whether your figures are very large or very small, computer is very highly capable machine. Even then you should know a little bit about the shortcut method also. The shortcut method, what in fact shortcut method does, that the given data is transformed in such a manner like here x minus xm minus xa from the middle values of the class interval, which are x1, x2, x3, xm. You take any arbitrarily chosen value in the middle of the x. Let us assume that it is xa. Then take the deviation of all the x middle values from that chosen value, and if you have a equal class interval, then divide it by that class interval also. So, all these deviations will become smaller, will get compressed, and your values, xm values will get converted into new values. Now, this transformation is known as change of origin and scale. When we subtract each value from xa, this is known as change of origin. Now, when we divide them by h, that means we are changing the scale. So, this whole combined together is known as change of origin and scale. These are known as step deviations. The values now what we get are known as step deviations. Now, suppose these step deviations we call them as d1, d2, d3 and dn. Then you apply the same formula summation, instead of summation fm square, you apply the formula summation fd square divided by n minus summation fd over n whole square and work out the standard deviation of the step deviations. Now, it will be h time less than the original deviation because you have divided them by all the deviations by h. So, you do the reverse. Earlier you had divided, now to bring it back, you multiply it by h, you get the original value of variance by multiplying it through h. So you get sigma is equal to h and the whole thing as given above. Then let us explain it by taking an example also. We have given here a data for 173 years for Cherrapunji, the rainfall data. Some days are dry days, so you take them out, 173 days are left only. We use Microsoft Excel. You can also, as a exercise, as a practice, you can use Excel. Excel can help you in a number of ways. In all the three methods we have calculated through Excel. The figure, the data has been shown on a graph paper, and then the calculations are made. This is the total rainfall, number of wet days 173, arithmetic mean 85.090 millimeter, mean deviation 87.895 millimeter, standard deviation 129.122 millimeter, variance 16672 point. You take under root of variance, you get the standard deviation. Now, the same table of 173 days observation can be converted into a frequency table also, and when we worked it out using all the formulae given above, you find that the mean deviation, mean daily rainfall, is slightly different from the ungrouped data. It is 105, earlier it was 89 something. So the difference is because of the error which we incur while converting ungrouped data into grouped data. Similarly, there is some deviation in the standard deviation and the variance data also, but they are quite close to each other. Of course, when you use algebraic simplification and without algebraic simplification, you get the same results. It's only when you convert the ungrouped data into grouped data, you incur into some loss of information, which will be reflected in the discrepancy in the parameters mean. So you see that the data given above shows a quite significant value of mean standard deviation. Either way you measure it, there are significant differences in the result, as standard deviation is 160, more than 30 millimeter higher than is calculated by using simple method of ungrouped data. Even mean daily rainfall also deviates significantly, as it is 105.2 by using frequency formula instead of 85. So there is quite a big difference. The common use of the standard deviation are in the following paragraph. Standard deviation is the absolute value of variation measurement of a distribution. If there are two or more distributions, to compare their variations, the measures of relative dispersion, which is standard deviation dependent, are used. See, basically you should be very clear about standard deviation, that a standard deviation, although measures the variability, but it measures the variability in absolute term, meaning thereby that it does not attach any significance to it, that is, whether it is a highest variability or it is a low variability. There is no high variability, no low variability in a standard form. the concept of variability depends in fact on the consequences of variability on the geographical phenomena for which it is being measured. So, say for example, if you take rainfall variability in Rajasthan, which suppose comes out to be say 40 millimeter, and you take the rainfall variability in terms of standard deviation, you find is equal to say 50 millimeter. So, as in absolute terms, the rainfall variability is high in Assam compared to Rajasthan, but in terms of the scarcity of rainfall in Rajasthan, a variability or a standard deviation of 40 may be very serious variability, whereas in Assam a standard deviation of 50 millimeter or 55 millimeter may not be a very serious problem for geographers or for climatologists or for agriculturalists, because already there is so heavy average rainfall. So, you can evaluate the you cannot evaluate the variability with the help of standard deviation alone. You have to bring into consideration the average also. So, you have instead of the absolute measure of variability, we have relative measures of relative variability, which is in fact the standard deviation divided by the mean. That means how serious or how the standard deviation is placed in comparison to the mean value, which is known as coefficient of variation. It is simply defined as standard deviation per unit of mean. Now, you can compare standard deviation by taking its ratio with the mean. Standard deviation and mean are used to standardize the values of a distribution also, which is known as Z transformation of distribution, is where the actual variable, suppose you have a variable x, you have its mean value available to you, you have its standard deviation available to you. Now, the problem arises in fact that when you deal with multivariate data, you have large number of variable x, each one of them have different value of mean, different value of standard deviation, and moreover each one of them are measured in different units. Say for example, if you have 4 or 5 variable, one is the say agriculture production in terms of tons, then you have another variable is rainfall, which is in terms of millimeter, then you have the consumption of fertilizer, which is in terms of kilograms, then you have the credit to the farmers, which is in terms of rupees. Now, you have 4, 5, 6 variables, each one of them carrying different unit of measurement. Now, at later stages, when we compare them in number of ways, say, then each one of them has different standard deviation, different means. Their comparison, they are not comparable, they cannot be added together, they cannot be compared together, and some of them may have very high standard deviation, some of them may have low value of standard deviation, some may have very high mean value, some may have very high low mean value. All these problems pose serious questions before the social scientists. Geographers also face the problem of the unconformity of the variables. So, it has been suggested that before going for any kind of multivariate analysis, the variable should be brought to a common platform in terms of common mean in terms of common standard deviation, and they should also be converted in another variable in such a manner that they can be added or subtracted also. Now, as it is, we have problem of scale and we have problem of the unit of measurement also. So, what has been suggested to convert each variable into a standardized form in which they have 0 mean and they have unit standard deviation. This can be done by transforming variables into new variables. They are known as this transformation is known as Z transformation, and variables are converted into Z scores. How the X variable is converted into a Z score? Now, let us take one example of one variable. If you have a variable X, you find out its mean value, you find out its standard deviation value, suppose it is X bar and sigma, then from each and every value of X, you subtract the mean value, and whatever deviations you get, divide them by their standard deviation. You do it for all the values of X. Suppose you have 50 values of X, you get 50 transform values, call them 50 Z values at Z1, Z2, Z3 up to Z50. So, what will happen? That Z scores will be some of the Z scores which are less than mean values will be negative, and some of the Zx values which will be more than mean values, their Z scores will be positive. This is one thing, that roughly half of the Z scores will be carrying negative sign and half of them will be carrying positive sign. And as you know, the deviation of each value from the mean value when is added will give you 0, summation will be 0. So, you work out the mean value of this, it will 0 upon 50, which will be 0. So, the Z transformation will become such that the value of the variable Z will, the mean value of the variable Z will be equal to 0. Similarly, standard deviation will also get divided by sigma. So, if earlier standard deviation was sigma, the transform standard deviation will be sigma upon sigma, that is equal to 1. This transformation will happen with every variable of X. So, if you have a 5 or 6 or 10 X variable, you convert them into Z score, you get 10 Z score, such that the mean values will be 0 and standard deviations will be 1. This is used for mapping the distribution and areal comparison of geographical attributes. Also, it is used to study the probability of events occurring in a large after normalizing it and to predict the values of the specific observation. So, using the properties of normal distribution, we can find out, you will find out the properties of normal distribution, that within mean plus 1 standard deviation, 68.23% of the observations will fall. Within the range of mean minus 1 standard deviation to mean plus 1 standard deviation, 95.45% observations will fall, and within the mean plus 3 standard deviation on either side, 99.73% observations will fall. Other statistical techniques like skewness and kurtosis. Most important techniques, namely the analysis of variance, has been developed taking standard deviation as basis, which would be described separately in different modules. It is important to note that the variations of different sets of data containing different number of observations may be added together to analyze the combined variations of different attributes. For example, there are two sets of data having mean 1 and 2 standard deviations, sigma 1 and sigma 2, and observation as n1 and n2. Now, here we are going to explain you that if you have two distributions with all those parameters given above, how to find out a combined standard deviation. A combined mean is very simple. You multiply mean by number of observation in one case and mean multiplied by number of observation in second case. You add them, it will be the summation of total number of observations divided by total number of observation n1 plus n2, you get the combined mean. But if you have standard deviation 1 and standard deviation 2, then you can get a combined standard deviation by n1 multiplied by first standard deviation plus n2 multiplied by second standard deviation plus d12 and d22 divided by n1 plus n2 divided by 2, where d1 is equal to the first mean minus the grand mean, d2 is the second mean minus the grand mean, that is the combined mean x double bar. Measures of skewness, as described earlier, statistical moment is the mean of the first power of the deviations, that is the spacing of the size, class or individual in the distribution from the mean. First order deviation is simply the mean deviation due to its unit power function. It is first moment above the mean. Likewise, higher moments are defined by raising the power up to r. Note that second moment is variance, while horizontal movement above mean known as skewness and vertical moment is known as kurtosis are related to third and fourth order of moments. The moments are given as shown here. This first order, second order moment, this is the third order moment, fourth order moment. The skewness can be calculated from frequency distribution by using the 3 times difference between mean and the median per unit of standard deviation as shown here. In fact, in a skewed distribution, its maximum value can rarely be approached to +3. Of course, if mean is higher than the median, skewness will be positive because the mid value is higher than the value of the mid position. Increase in the case for the negative skewness. Further skewness coefficient, as Pearson's termed it, beta 1 is as mu 3 divided by mu 2 cube, mu 3 square divided by mu 2 cube. Measures of kurtosis. The kurtosis coefficient beta 2 is, that is the kurtosis coefficient, is equal to fourth moment divided by fourth power of standard deviation. It is the ratio of the fourth moment with the fourth power of the standard deviation of a distribution. As median coincides with mean, the kurtosis k is 0. Inversely, there is maximum range of beta 2. So, k is equal to beta 2 minus 3, which has 3 conditions. If beta 2 is greater than 3, this k is greater than 0, then curve is more peaked than perfect symmetrical curve called leptokurtic curve. If beta 2 is less than 3, that is when k is equal to less than 0, the curve is platokurtic curve is narrower is narrow, lower peak than symmetric. It will have a lower peak, and if beta 2 is equal to 3, k is equal to 0, curve coincides with normal distribution, no abnormality in the distribution, vertically skewed distribution, blue line in the curve given above, below, you can find the kurtosis, the skewedness, both positive as well as negative, and kurtosis also leptokurtic or platokurtic distribution. Thank you very much. This is what about the measurement of variability and its different uses in characterizing a given distribution. In the next, we will talk more about normal distribution and its properties. Thank you very much.